Hello everyone, Namaste. I am Ramnath who would like to present to you part 1 of the series on key learnings from chip development. A few more parts of the same series will be shared across in the future. Sometimes it takes a lot of time to learn and compile information in a presentable manner, that too within a short span. So some delay might happen. Hope you will understand this. As you all know, semiconductor technology development has been the key driving force for computing power increase in the past 30 years. As we know, the planar CMOS transistor has been the most widely used technology and node. However, as we know now that 5 nanometer is the advanced process node, and however the 2 nanometer is also coming into picture in these days. Before we go into the development of the sub-nanometer, we will just briefly discuss about the how it evolved. So at 20 nanometer, the planar transistors hit a wall due to short channel effects. Because of the short channel effects, the transistor performance will become unpredictable and difficult to control the yield. Hence, there were multiple developments happened in variety of sectors, either in the material science or in the tool development or in the materials and the processing tools. Okay, say that is when the UV lithography has been added. All these several modifications have been proposed. So Intel moved to FinFETs from planar technology in 22 nanometer. Other foundries also moved to FinFETs in either in 60 nanometer or in 40 nanometer. So in the FinFETs, actually, if you observe, the current is this is the FinFET, and this is the FinFET. This is the usual planar transistor, which many of us are more familiar. So in the FinFETs, actually, if you observe, the gate here will control the fin here in three sides. So this is one side, this one is another side, and the other side is third one. So thus three sides of the fin will be controlled. This is fin is basically, you can think like, assume that this is a fish-like structure. Then this is one fin, there will be another fin parallel to this, there will be another fin parallel to this. So you can consider that this is a fish and there are multiple fins for this one. So, so in this fin structure, the control on the current flowing will be much better controlled. Hence, the leakage will be less compared to planar transistors. So this is what has happened from 22 nanometers and all the way up to 5 nanometers. Coming to 3 nanometers and 2 nanometers and all, even this could not handle. So they moved to other improvements in the gate, and this is called gate all around. That means, like, if you see the fin, this fin is connected and controlled by the gate in all directions. If you see here, gate surrounds the fin in all four directions. If you see here, this is multi-fins. So here, this is surrounded by gate in all directions. This is called nanosheets or nanowires based on the thickness. So thus the FinFET and the gate all around FinFET became the new modification, which kept the short channel effects coming into the yield issues. Thus, all these things have helped the transistor to function in a predictable manner. Coming to the next part, uh, aside to this one, semiconductor industry globally needs 1 million more workers by 2030. This is why, because there were 73 fabs have been either newly added or newly revamped. 20 out of the 23 are newly revamped. Majority of these 23 are either in 28 nanometer or larger than 28 nanometer. And there were definitely few advanced node fabs. All these things needed more workers. So they are counting that by 2030 there will be around a million more workers maybe needed in the from the semiconductor industry. So this is will also lead to more economy. So the market will also grow from currently close to 500 to 700 billion dollars to all the way up to cross $1 trillion. So all these things are good situations with the semiconductor ecosystem. Aside to this, there are some other items which we will discuss, which are affecting the semiconductor ecosystem. In the recent past, the semiconductor ecosystem landscape is continuously changing. If you see, the unusual circumstances took place. The main one is the COVID-19. This has changed the working patterns. The customer behavior has changed, the business revenues plummeted, and corporate operations also significantly got modified. And people have also some people have lost their lives. So all these things have really affected the way of work. And as you know, work from home culture has crept in, and it has changed the way of modalities. Because of this, security upgrades have to be done to protect the IPs. And because of the less movement in the society, because of the COVID, the auto vehicles sale has also reduced, and also because of the semiconductor supply chain breaking, because of the restrictions, it got affected too. So many reasons have taken place, and then the each vehicle, say for a car, there are close to 2,000 chips or more will be there, semiconductor chips will be there. So like that, the demand has reduced, and all these things called for new way of working, and also change in the modalities, and new processes to handle the system. Okay, and aside to that, it we also see recently destabilizing wars. This also led to destabilization of the semiconductor supply chain. So this happened, whatever we are seeing at country level. How much ever we cannot control this one, but at company level, I can say that we have a role to play, and across teams in the same company. Say, for example, between RTL verification team or physical design team or the timing team or the manufacturing team, all these things, you need to act like you are one, and then you need to ensure that there is transparency among the teams, and there is a sharing of knowledge freely across, and you should not hold the data to yourself, and you should not create walls across your team and the other team. So that way you can reduce the wars, and you can improve the supply chain. Okay, it is not only at country level and even at company level. And I want to take one extra minute and want to mention that even at personal level, you will have to win over yourself at multiple levels. If you go based on your internal enemies, you can consider them as kama, krodha, moha, madha, lobha, matsarya. Okay, you can refer in the Google on these matters. I would say like you need to fight with these wars because these are the desires how they will constrain you from becoming into a spiritually elevated person. Okay, so you need to ensure that all these things you, at various levels you have a vibrant and enabler role to play and try to meet to and reach that goals. Coming to the other change happening in the semiconductor ecosystem is the disruptive technologies. So as we have illustrated, figured out, the based on the years, we have seen that there are several technologies have been changing, and the modifications have happened to ensure that the cost and the product efficiency have been improved, and 3D IC and quantum technologies and 5 semiconductor introduction, carbon nanotubes coming, and aside to that, in the EV side, EV vehicles have come replacing the fossil fuel vehicles as much as possible, and the hydrogen vehicles have also come into play. Like that, new way of systems have also come. These are all the disruptive technologies. So all these things definitely need semiconductor chips, and more. All these things demand has increased based on this. Aside to that, we also need to know that security has need to be revamped and need to be increased, because they, if you see the quantum technologies, the encryption, the current encryptions and all those things can be easily broken by quantum technologies, and quantum chips are not the things of the what do you call, like down say 30 years, 40 years, like that. It is in the near future, maybe 5 to 10 years, we will be having real quantum chips, working chips and all. So already many people, many companies are already on that activity. So given this, there is a demand, and there are also disruptions and unknown situations are happening. So what we need to do at our level is, we need to say 3D IC, as I was mentioning, this also we need to is a disruptive technology. At our level, what I can say is like, we need to improve the holistic learning, in the sense like we need to learn not only our specific domain of interest, we should also learn the neighboring domains, so that how the data flows and how optimally, by working with the neighboring domains, we will be able to influence the smooth way of data processing, data flow, and also efficient way of data flow also can be enhanced. So this is why holistic learning will really help. Aside to that, also promote as much as possible the industry university connection, and gain out of this industry university partnership, and also make an enabler for the university and your members of that to grow along with you. And it is in the near future on are happening. I would say that we need to uh, embrace the AI, either in GNNs or the RLs, whichever. That means like graph neural networks or reinforcement learning, whichever way you employ the algorithms and all. So we need to use it in our existing way of chip development. So if you want to hear about the graph neural networks, how it works based on the graphical manner. In the sense like it will decompose the system into multiple nodes and edges. So in our chip design also, you can think that circuit will have a node and it will have a net. So net, you can consider that as an edge, and a node you can consider say basically a drain of one uh, m- uh, as one node and a gate of another device as another node, and in between there is a net you can consider as edge. So this graph which has been represented, you can consider that this will need to be optimally created by these AI tools by ensuring the functionality will not be destabilized or will not be affected. So that way they will try to make it. And as I was mentioning, the companies like yeah, NVIDIA and other companies, EDA companies like Synopsys, Cadence, and Siemens, all these companies are already using AI tools, and thus they are leveraging these methods to improve the efficiency. Okay, even the MIT tools, they are also using AI to make the chips perform much better than in manual way of generating. So this is the new disruptive technologies, and the landscape is continuously changing. So we need to adapt to the new flow. Every successful endeavor, whatever you consider, starts with a clear specification, and chip development is no exception. A semiconductor product generally begins with marketing requirements for a new product, which defines what the product will do, how it will be used, what are its interfaces, where it will be used, and what performance metrics it should meet. This finally culminates into a chip itself or a system incorporating the chip. As we know, the design of a product for hospitals, data centers, banking, military applications, toys, etc. differ in operational performance, power consumption, and in other aspects like design area. So hence, where the product gets used also make a big impact on chip specifications. Thus, as you realize, specifications and requirements are indeed the soul of the chip, and these specifications need to be informed to all levels of chip development teams so that they will take appropriate uh, choices and also may question the authenticity of the specifications, as the chip specifications are not written on stone and they keep evolving over the project execution phase. Okay, so adding clocks, resets, power management features, and testability support to the design may also require unanticipated specification updates. This one needs to know and should take appropriate measures and be open to the change on these fronts, because product ultimately benefits. If we go back onto the architecture phase, I will not describe each of these blocks, but broadly describe, and will consider the specifications section in detail in the following slides. So architecture exploration deals up with coming up with the suitable system architecture and distributing the system tasks in the specification onto those components or intellectual properties, blocks, and realizing them with the carefully chosen technology. This technology need not be either 28 nanometer technology or 140 nanometer technology or 5 nanometer technology. It depends upon the cost to be consumed by the chip. So thus the system architects develop a high level specification for the chip, typically including both aspects of the hardware design and the associated software. Sometimes the software and the hardware may be intertwined, and some of the parts of these hardware and software may be independent. So based on the usage of the product vulnerabilities, we also need to remember that system architects will identify the potential security threats and plan the measures to mitigate them accordingly. Using product specifications and requirements, a functional model is developed which relates a system output and inputs. This functional model is gradually refined into an architectural model where architectural components communicate at the transaction level. The architectural model hence can be further refined into RTL, which can be implemented in silicon through logic synthesis, physical design, physical verification, and other steps which lead to tape out. After tape out also there are so many other steps like wafer fabrication, wafer level testing, packaging, etc. These are also top level tasks which play a crucial role in the final chip development. These will be discussed in the coming parts of the series. No matter how complex a system becomes, the need for effective communication and collaboration among the various stakeholders who share the development of the chip will play a major role, and this should be considered for the success of the product development. References which helped me in arriving at these slides are provided here. Feel free to look at them. End of part 1.